Okay, welcome back to Real Analysis. In this short section 7.4, we're going to talk about the continuity of the derivative. That is, when a function is differentiable on an interval, then you get a new function, its derivative. And we can ask the question, well, what kind of properties does that new function have? And in particular, in this section, we want to ask, is that new function, is that derivative itself always continuous? So we're gonna ask and answer that question in this lecture. And in fact, you can already see that we're going to show that the answer to the question is no. All right. So kind of starting from the top, let's recall what we've already proven, theorem 7.6. Theorem 7.6 says that if a function is differentiable at a point, then it's continuous at that point. So in particular, if you have some function f that's differentiable at every point on an interval, then that function will be continuous at every point on that interval. Or just briefly, differentiability implies continuity. Yeah, we've seen examples, and you should stop the video right now and recall what the example is, that the converse of that theorem doesn't hold. A function can be continuous at a point without being differentiable at that point. So differentiability and continuity are not the same notion, right? So in this lecture, we're going to show by an example that it's possible that a function be differentiable. That is, that the derivative f prime exists on some interval. The example I'll give, the interval is the entire real line, but that derivative need not be continuous. Okay. So in more advanced classes, maybe in the fall course for Math 416, we can talk about so-called continuously differentiable functions. That's a very important class of functions that are not only differentiable, but their derivative is continuous. But here in this section, I'm going to show you by an example that not all functions are so-called continuously differentiable. Okay, so we're just going to proceed by giving a specific example. So here's the example I want to look at. I'm going to define a function again on the entire real line. So the interval is the entire real line. And that function, I'm just going to scroll up a little bit here. It's piecewise defined. It's the product of x squared and sine of 1 over x. Oops, little typo here. I can just fix it on the fly. That's if x is not 0. Okay, so if x is any number other than 0, then this function is given by x squared times the sine of 1 over x. If x is 0, I just define the output to be 0. Okay, so that defines a function on the entire real line. If you take an element x that's not 0, then the function is governed by this formula, x squared times sine of 1 over x. And temporarily assuming that the sine function, like we've done many times, is differentiable, then you can use the differentiation rules. I think you'd have to use the product rule, the power rule to differentiate the x squared part, and then the chain rule to differentiate the sine of 1 over x. 1 over x is x to the minus 1, so another power rule. So if x is any number but 0, I'll leave it to you. You can stop and check my calculation. But working out that derivative with those rules gives us this expression. Okay, I won't read it out loud, but there's an expression for the derivative f prime. And again, that's if x isn't 0. Okay, I want f to be differentiable on the whole real line, so I have to tackle the derivative at 0, but the formula above doesn't govern the function when x is 0, so I have to do it by definition. So if you want to calculate the derivative at 0, we have to proceed by the limit definition. Okay, so that's what I'm going to do. The derivative of this function at 0, if it exists, is given by this limit, the limit of the difference quotient. But f of 0 is 0, so what we have to do is take the limit of x squared times sine of 1 over x divided by x. Simplifying it a little bit algebraically, we have to take the limit of x times sine of 1 over x, and that limit is 0 by the squeeze theorem. I didn't include the details here, but I'll let you check it out, that the function x times sine of 1 over x is bounded, for example, between negative x and x, both of which have limit 0. So this thing has limit 0 by the squeeze theorem. Okay, so that gives us the differentiability of this function f on all of R. Here's a formula for it, right? Because like we said, if x isn't 0, the derivative is given by this kind of linear combination of those two trigonometric functions. And we just computed if x is 0, the derivative is given by 0. So f is a differentiable function. F is a differentiable function, and there's its derivative. A corollary, f is continuous. F must be a continuous function on all of R because it's differentiable on all of R. But what about the continuity of F prime? That's what we want to check out. I claim that F prime is not continuous. Right? So that's the whole point of this lecture is I want to give an example of a function. It's differentiable on the entire real line, but its derivative itself is not a continuous function. And F will fail to be continuous, I claim, at x equals 0. And I'm going to prove that with a sequential argument. I'm going to use the sequential criteria for limits to prove that this function isn't continuous at 0. I know what its value is at 0. The value at 0 is 0. Right? So if it were continuous at 0, the sequential criteria for limits says that any sequence approaching 0 in the domain would have the image sequence approach 0 in the codomain. Well, I'm just going to strategically pick a sequence that's approaching 0. For any natural number, I'm going to let xn be the reciprocal of 2 pi n. All right, so it's the reciprocal of the integer multiples of 2 pi, if you like. That's a positive number. I can emphasize it here for every single n. That xn is a positive number. And it's clear, I'm going to leave the details to you, but it's because 1 over n goes to 0, so any multiple of it, 1 over 2 pi of it, also goes to 0. So I didn't cite the exact limit laws, but by this point in this course, we can just say such things. That sequence is clearly approaching 0 as n goes to infinity, but if you plug that sequence into our function, you look at the so-called image sequence. And here, pardon me, I'm not plugging it into the function, another typo. These notes were not carefully constructed. I'm plugging it into the derivative, f prime. And since xn is positive for every n, the formula that I'm plugging it into is the one that I'm underlining, right? So if I plug xn into f prime, what do I get? Well, I get 2 times x, that's xn is 1 over 2 pi n, the sine of 1 over x, so that's sine of 2 pi n, and same for the cosine. But you know from trigonometry that the sine of any even multiple of 2 pi is 0. So this first term is gone. The cosine of any even multiple of 2 pi is 1. So this image sequence is constant. It's equal to -1 for every n. Well, a constant sequence has a limit, and its limit is its constant value. So the image sequence converges to -1, but that's not f prime of 0. Okay, so that proves it. F prime is not continuous at x equals 0. So that's really the end of the point I wanted to make, is that there are examples, there's others, but just this one is particularly nice, though the work can be done kind of quickly, to illustrate that it's possible that a function have a derivative of it at every point in an interval. In this case, it was the entire real line, but that derivative fails to be continuous. Just going to kind of end the video by showing you some images that I created of this function f of x. So drawn on the left here is the function. The font is kind of small up here in the kind of title, but that function x squared times sine of 1 over x, that's our f of x. Well, it's given by that formula. If x isn't 0, its value at 0 is 0. It's a differentiable function. It's kind of interesting. I mean, what am I doing? We're taking that sine of 1 over x function we've looked at, the thing that oscillates sort of more and more near the origin. But by multiplying it by x squared, we're kind of dampening it by this quadratic function. And in fact, it dampens it enough that it's sort of smooth at the origin. So those waves are getting, the amplitude of the sine wave near 0 is getting smaller and smaller, but it's doing it in a way that there's a tangent line. There's a well-defined tangent slope at every point. That's what we proved. It's kind of an interesting looking function. Okay, over here is its derivative. It's not so nice looking. The derivative f prime, well, I plotted this with the formula when x isn't 0. Remember, the value of the derivative at 0 was just 0. So you have to imagine that at the origin, this derivative's value is 0. And this picture shows that it's clearly not continuous at x equals 0. Right? This thing is oscillating kind of infinitely fast in every neighborhood of the origin. So there's a picture of the derivative. What I've drawn down here, these blue dots, those are the images of the sequence that we looked at. So the x coordinates of these blue dots, if I change my laser pointer color, the x coordinates of these blue dots are our 1 over 2 pi n, okay? And they all have output -1. So the x coordinates of those blue dots is converging to 0, but the y coordinate is not converging to f prime of 0. So f prime is not continuous at the origin. Okay, thanks for listening.